Hey everybody, Dr. A here, and in this video we're going to briefly discuss how to compute the shear modulus from a non-destructive torsion test. Now, a non-destructive torsion test is a very common laboratory type of test that you might perform in either a mechanics of materials or a civil engineering materials or even a structural analysis laboratory setting. Now, when we say non-destructive, we mean that we are not damaging or destroying the specimen, okay? So we're going to make a note of that. Non-destructive basically means specimen is not destroyed, okay? Now, typically, we deal with destructive tests, like when you perform a compression test on a concrete cylinder, or maybe you perform a tension test on a metallic specimen until it fails or fractures. Those are called destructive tests. So in this video, we're talking about a non-destructive torsion test, okay? Now, how do we do that? Well, basically what we do is step one, we obtain a shaft specimen and measure its diameter and length. Okay, so typically to perform a non-destructive torsion test on a particular specimen, you're going to have a circular shaft specimen. You know, the cross-section may look something like this, and often they're solid cross-sections. So this is going to be the cross-section of your specimen, and then, you know, the length of your specimen will have some kind of length like this, and you know, we'll have a length L, and of course, you know, you're gonna have a diameter here, diameter D. Okay, and so what you do is you set the specimen up inside of some type of apparatus. Now, there's all kinds of apparati or apparatuses out there that you could use to mount your specimen in, okay? So in step two, I'm just going to be kind of generic. I'm going to say mount specimen in apparatus in which we can apply a load to cause the cross section to twist at one end with respect to the other end. All right. Now, the way you typically do that is you're going to mount your specimen in some type of load frame or framing apparatus. And here's our cross section again. Okay, so here's our cross section. And what you're going to do is you are going to, the apparatus will somehow have an attached lever arm that comes in contact with one side of the specimen. So I'm going to put this little bar here, and I'm going to make a note here. I'm going to say this right here is called a lever arm, okay? And it's going to have some length or some distance, little d, okay? Now, what you do is you apply a force at the end of the lever arm. Let's call that force F. And what that will do is that will cause your specimen to tend to twist, okay? It will tend to twist and rotate. And so what will happen is that lever arm will rotate in a fashion like this, and I'm going to draw kind of the center line here. And so you're going to have this rotation angle right here. Well, that rotation angle is, guess what? That is your angle of twist phi. Okay, angle of twist. Now, depending on the apparatus you have, that angle of twist could be directly measured, or you might have to mount up some other dial gauge. For example, you might have to mount up a dial gauge right here where you're going to read off this vertical deflection, for example here. Call this little delta maybe. And then you can use small angle theory to relate delta, phi, and little d right there. It just depends on the apparatus. At the university I work at, Christian Brothers University in Memphis, Tennessee, we typically mount up a dial gauge right here at the end of this lever arm, and we directly measure this vertical displacement, little delta, and then we use small angle theory on this little right triangle because it's a very small rotation, and we're able to get the angle of twist by a calculation using small angle theory. But what we would directly measure is delta. But you could have another apparatus where you could measure the angle of twist directly. Nevertheless, you either get the angle of twist phi directly, or you get it from a simple calculation of a direct measurement of little delta, okay? So what do we do next? Well, we remember that, that step 3, we remember that the definition of angle of twist of one end of a shaft with a constant cross-section and constant material properties is given as phi equals TL over JG, okay? And so again, remember we've got a prismatic section, which again, if you remember some vocabulary, prismatic means you have a constant cross-section. In addition to that, we're going to assume we have a constant material property, so G is the same throughout the length of the specimen. And so what we can do is we can quickly rearrange this, and we can get G equals TL over J phi. Now, if you remember your knowledge from mechanics of materials or CE materials, material properties, whatever, what are all of these values? What are each of these values? Well, L right here is the length of the specimen, right? That's the length of the specimen we saw earlier because we're rotating one end of the shaft with respect to the other. So the whole length, it's going to rotate through the whole length. T is the torque that's developed in the cross-section due to the applied force at the end of this lever arm. So what you could do is you say T, that torque T is here, and I'll make a note here. We can compute T as equal to the force F times the lever arm. Now, depending on how big your cross section is, if you have a specimen that has a fairly big cross section, then what you really need to include there is the lever arm distance little d plus the diameter over 2, because you really want to look at rotation about the center point right here. But if you have a very small, thin cross section, typically this d over 2 isn't going to make that much of a difference. So I'm going to make a note here. I'm going to say if the lever arm d is quite a bit longer than the diameter d of the specimen, then you can just say T equals F times little d. So just be on the lookout for that. If you have a wide cross section or a large diameter cross section and a small lever arm, then you're going to need to incorporate this little d plus the diameter of the specimen over 2. Otherwise, if your lever arm is much bigger than the diameter of your specimen, you can just say that the torque developed is equal to force times the lever arm little d. So that takes care of capital T, capital L. We already talked about the angle of twist phi. And what about this value J here? What is J? Well, if you remember, J is your polar moment of inertia of the cross section. And sometimes this shows up as I sub z, okay? The moment of inertia about a z-axis or the pole of the cross-section. So that depends on the shape of the cross-section. Oftentimes we deal with circular shafts, so that would be pi d to the 4th over 32. So we're going to say J is equal to pi d to the 4th over 32 for a solid circular cross section. So that takes care of J. One last comment on phi. Phi is the angle of twist. It's going to have units of radians, okay? So you want to make sure phi has units of radians. And then finally, you'll end up calculating G, which is your shear modulus, which is a material property of the material that shaft specimen is made out of. Now, I would suggest you run multiple iterations of this. You run this test multiple times, maybe run it multiple times with different loads, and you can actually generate a plot if you're assuming linear elastic behavior and your loads are not so super heavy to cause any permanent deformation. Then you can make a nice linear plot out of this, and then you can get the slope of the line that passes through your multiple data points as G, okay? But for a quick one hitter, basically, you can just run this once and get an estimate of G. But again, it's always good to run multiple iterations. And this is a non-destructive test with most likely you're going to be using low magnitude forces here. So you could run this multiple times pretty quickly and increase your accuracy and your precision in what you're doing. And of course, in a laboratory experimentation setting, it's always good to run multiple tests, especially when you have the time to do it. So this concludes this video. Again, this is a video just to give you a quick overview of how to calculate or determine the shear modulus of a material that is made into a circular shaft specimen by performing a non-destructive torsion test. Hopefully you found this video helpful. Please hit like and subscribe and be on the lookout for more information like this. Thanks for watching.